Hi everyone, welcome to week 3. In this lecture, we're going to motivate the inductive logic project by showing you some common ways that humans make mistakes. These are mistakes in reasoning, and what the inductive logic system is going to allow us to do is to make less of these mistakes. So let's get started. So just as a refresher, remember that our inductive logic takes an argument in natural language, right? We translate that argument, we put in the inductive logic, and then the inductive logic hopefully spits out an inductive probability of the argument. So that is a very abstract way of seeing what inductive logic will allow us to do. And we saw what are the two problems of inductive logic. One is to actually construct the inductive logic house metaphorically. And the other one is how to rationally justify the use of one inductive logic versus another. And remember that in last lecture we saw Hume's problem of induction, in which Hume argues quite convincingly that there's no rational justification for picking one inductive logic over another. Or another way to see it is that Hume argues that our inductive practices, which we use all the time, these are not rationally justified. That should be concerning. But what we're going to do in this lecture is show you some cognitive shortcomings that we often make as human beings and see, okay, maybe we can't justify induction in this abstract way. However, we can note some ways that we reliably make mistakes, and we want to not make mistakes in these cases. And that's what inductive logic is going to allow us to do. Okay, so here's a refresher still. Remember that formulating rules for validity was rather easy. It's a yes or no affair, right? You have an argument, and it's rather easy once you have the tools of truth tables, etc., to figure out whether the argument is deductively valid or invalid. But formulating the rules of inductive logic seems to be much more difficult, and we'll see a little bit more of that today. And inductive logic poses this problem, which I mentioned, is that we're not even sure that we can justify or rationally justify the use of an inductive logic. So what was Hume's solution? Again, this is a refresher from last time. So Hume thinks that we ground our knowledge by custom, not by reason. So he says that all inferences from experience are affects of custom, not of reasoning. This is a passage from one of Hume's most read books, which is the Treatise of Human Nature. And it's a nice passage, I think, worth looking at. So he says, custom, then, is a great guide of human life. It is that principle alone which renders our experience useful to us and makes us expect, for the future, a similar train of events with those which have appeared in the past. So what Hume is saying to his problem of induction is he's saying, look, it's not really a problem. We just, by habit, make inductive inferences. And it works well, there's no rational justification, and that's fine. We shouldn't try to rationally justify it. Now, one way to read this is that he's kind of throwing his hands up in the air and saying, look, there's no justification, whatever, that's fine. We shouldn't try to revise our practices, our inductive practices, to reason better. But this is not what we're going to do. So the main question we're going to ask in this class is, how should we form reliable beliefs? So a key idea of this class is going to be, look, we're going to agree with Hume that we cannot get ultimate foundational justifications for beliefs. But what we're going to do is kind of sidestep this question of whether there's a universal rational justification for our inductive practices and go to a smaller, maybe local level. We're going to show that we can form beliefs in ways that we will take to be reliable. And we'll see this with our system of inductive logic, which we'll introduce in the next lecture. And the second key idea of this course, which is related to the first one, is that while we can't get this global foundational justification for our beliefs, we can get local justification. And we'll have reasons for thinking that locally these beliefs are justified. And the strategy we're going to do, or use, is to try to distinguish between reliable and unreliable methods of forming beliefs. And what we're going to do today is to see what are unreliable methods of forming beliefs. Okay, so let's keep motivating this inductive logic project. So the goal for today is to motivate us to construct a scientific inductive logic. So why would we even want an inductive logic? What is the use of it? And how we're going to do that is to identify biases in our own reasoning that we will want to correct. So hopefully, I'll show you some examples of cognitive shortcomings that you'll see and say, wait a second, I don't want to form these mistaken beliefs. I want a way to make these beliefs better. And inductive logic provides a way to do so. Okay, so again, you might ask, do we really need an inductive logic? Can't we form a rule in inductive logic just like we did in deductive logic to figure out if a conclusion is guaranteed by the premises? Well, let's try. So let's look at this argument, this inductive argument. All observed emeralds have been green. The next observed emerald will be green. So notice that this is an inductive argument, right? Because I'm not saying all emeralds are green. I'm saying all of the observed emeralds have been green. Or another way to see it, all observed emeralds in the past have been green. So the conclusion is the next observed emerald will be green. So what we want in inductive logic to do is to get this argument, put it in the inductive logic black box, and output something like high inductive probability. Similarly, in this example of all ravens that have been observed have been black, therefore the next observed raven will be black. This is again a case of an inductive argument. So we want to put this argument in our inductive logic. And do you think this will be a high or low inductive probability? Well, intuitively, this is a pretty good argument. We would want it to give us, as an output, high inductive probability. So here's an exercise that I urge you to pause the video and think. Can you come up with a rule that will determine the inductive probability of this argument? Because that's what we want to do. So here's the argument. 10 out of 20 observed coin tosses landed on tails. The next coin toss will land on tails. What's the probability of the conclusion? Well, you might think that it's 10 over 20. In other words, that it's 50%. How could you come up with a rule that would give you or would output this percentage in your inductive logic? Well, here's an example of a rule that seems pretty intuitive. N% of observed x's have been y's. Therefore, the next observed x will be a y. That's a rule that seems that we could use as an inductive logic, or as a tool of inductive logic, to use on arguments to figure out their inductive probability. It seems pretty intuitive, right? So let's use it on the previous arguments. So in this one, where it says all ravens that have been observed have been black, therefore the next observed raven will be black. If we put this in our inductive logic calculator, and in this case it's rule S, what will rule S give us? Well, are we done? Rule S seems to be pretty good in that case, right? It seems to be giving us an inductive probability, namely 100%, that seems to correlate with what our intuitions would say about that argument. But we're not done. There are several limitations to such a rule. Okay, let me come up here to make some more space. Okay, so the first limitation of this rule is that it doesn't seem to apply in the way we want it to every form of argument. So look at this argument. 60 ravens have been observed. 95% of them have been black. Therefore, the next observed raven will be black. What does rule S tell you here? Well, it tells you that the probability of this argument will be 95%. But let's take another argument. 1 million ravens have been observed. 95% of the observed ravens have been black, therefore the next observed raven will be black. Rule S gives you 95% probability for the conclusion of this argument. But you'll see that one of these arguments seems much stronger than the other, right? It seems much more likely that 95% is the correct outcome or the correct probability that you want to assign to the argument if you observe 1 million of the ravens rather than only 60. And Rule S doesn't really allow to consider this. So that's one limitation. Another limitation is that it doesn't always assign the probabilities we'd really want it to. So look at this argument. 100% of observed humans have been featherless. The next observed human will be featherless. Rule S here gives you 100%. And that seems correct, right? I really strongly think that the next human that I'll observe will be featherless. But let's look at another argument. 100% of episodes of Barry, found on HBO, that Ben has watched have been in California. Therefore, the next Barry episode Ben watches will be in California. Rule S also gives us 100% in this case. But you'll see that the argument on the left seems very strong. 100% seems like pretty much the right probability. However, on the case of my watching of a particular show in California, being 100% the next time I watch the show doesn't seem as strong, right? I might be in the middle of the season and watch it today, but I'm not in California today. Here's an exercise for you. Pause the video and ask yourself, why would we want these to be assigned different inductive probabilities? Okay, let me move back down here. So the reason we think that the inductive probability of the featherless argument is a good one, whereas the Barry episode watching is not, is because all observed human have been featherless is a projectable regularity. Now we don't need to get really into the details of this, but I just want you to get the intuition of what a projectable regularity is. Namely, a projective regularity is a regularity that you observe in the world that you expect to hold as time goes on. All observed humans have been featherless seems like a pretty good candidate for that. The statement, all episodes of Barry Ben has watched were in California, is not a projectable regularity, right? You don't expect this observed regularity. It is a regularity, right? Because I have, right, if you have observed it, or I tell you, I have watched all the episodes of Barry in California, so it is a regularity in the world. But you don't expect that regularity to hold across time necessarily, because I might move, and if I move to Texas, say, then that regularity will immediately vanish. So an unprojectable regularity is a regularity that is more fickle or more fragile. Okay, we've seen Rule S, and we see that it doesn't really work as a universal rule for our inductive logic. Rule S is just one case, but constructing such a rule, even if you tweak it, is very difficult. And this is what the video that I posted on the new riddle of induction, namely with this Grue-Blein paradox, it's very difficult, if not impossible, to construct such a rule. So we kind of have to abandon trying to construct this universal rule in the same way that we have the rule for determining whether an argument is always deductively valid or invalid. Okay, so now you might ask, do we need an inductive logic? Can't we just go by our intuitions? We've seen that constructing this universal rule is very difficult, if not impossible. But another alternative say, look, we don't need such a rule. We could just go by our intuitions. Unfortunately, and this is what we're going to see for the rest of this lecture, is that humans are prone to a variety of errors and biases when reasoning inductively. Some of these that we'll see are the gambler's fallacy, the conjunction fallacy, and the base rate neglect. And what we're going to do is look at these fallacies and see, look, our intuitions of how to reason often lead us astray. And we can notice that they lead us astray. And what inductive logic will allow us to do is to lead us back into the right track. Let's look at the first fallacy that we'll see in the class. This is the gambler's fallacy. You might have read about it. So suppose I flip a fair coin, that is one that's always equally likely to land heads versus tails, 5 times. So this is any old coin you'll find at a grocery store or under your couch. Suppose I flip it 5 times and I get 5 heads. Heads, 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 heads. The question is, how likely is the next flip to be heads? Now, many of you might think that it's more likely for the next flip to be tails. And in fact, there's a lot of documented cases in casinos, for example at the roulette table, where something similar happens, where people would bet a lot of money after seeing a streak of what is equivalent to a bunch of streak of heads. And then people would bet thinking that the probabilities have to kind of adjust. And so the next flip has to be tails, right? And so there's a higher likelihood, people tend to think, that the next flip will be tails. But that's not true. The probability that the next flip is heads or tails, it's both 50%. Because what the previous flips have turned out to be, whether they were heads or tails, has no bearing on the next flip. The next flip is equally likely to be heads or tails. So here's a cartoon, which I think is pretty representative, of this person that goes to a grocery store and is buying a lottery ticket and says, I know the last 5 scratch-off tickets didn't win, which means this next one must be a winner. So that's really a textbook case of the gambler's fallacy, because it's not the case that if this person goes every week to buy a scratch-off ticket and every week they lose, that their probability of winning the scratch-off increases because the probabilities remain the same. So here's another way to look at it through 2 contrasting examples. In the first case, you intend to flip a fair coin 10 times. Ask yourself, what is the probability that you end up with 10 heads? In the second case, suppose you flipped a coin 9 times and ended up with 9 heads, and you know it's a fair coin. What's the probability that when you flip the coin one last time, you will get another heads? Well, in the first case, what's the probability that you end up with 10 heads? The answer is 1 over 2 to the 10th, and it's an extremely small number. It's extremely unlikely that you flip a coin and you get 10 heads in a row. Now, in the second case, you might have the intuition, well, if I flipped a coin 9 times and every time it landed heads, it's true that's an unlikely situation. But what's the probability that when you flip the coin one more time, you'll get another heads? Well, that's still going to be 50%. So the gambler's fallacy is a fallacy of reasoning that occurs when we see a dependence between propositions or events, when there's really independence. Okay, so now you might ask yourself, what does it mean for propositions or statements to be independent? Well, statements are independent just in case neither one provides any evidence for the other. So here's a more formal definition. So P and Q are independent when these arguments have the same inductive probability. So if the argument P then Q and not P then Q have the same probability, then these 2 events, P and Q, or these 2 statements, are independent. So try to figure out an example before I give you one. Okay, here's one. I drank a glass of water today. That's true. Therefore, Biden will rerun for presidency. I don't think that my drinking a glass of water today has any bearing on the probability that Biden will come back and rerun for president. But I did not drink a glass of water today, therefore Biden will rerun for president. That has the same inductive probability as the other one, right? Because my drinking a glass of water or not has no effect on the conclusion of Biden rerunning for presidency. So again, the gambler's fallacy occurs when we see dependence between propositions when there's really independence. So in the case of flipping a coin, we see a dependence, right? We see if I flip heads 5 times and I ask you what's the next flip going to be, many people tend to think, well, the probabilities have to readjust, and so they're dependent, the next coin flip is dependent in some way of the previous coin flips. But that's not true. Every case of flipping a coin is independent. So here's the takeaway. We need to be very careful about assessing the independence or dependence of chance events. And our inductive logic, we'll see, will help us do that. But note, sometimes chance events are not independent. So we have to really be careful of judging, are the events independent or not? For example, wars aren't independent of each other. Whether Russia goes to war with Europe is not independent of whether Russia goes to war with the United States, right? Because of all sorts of geopolitical factors. So there's many events in the world that are not independent. But the key to good reasoning is figuring out, well, what kinds of events are independent or not. And in cases like the gambler's fallacy, paying attention to that will allow us not to make mistakes. Now let's look at another example of another fallacy. We've done the gambler's fallacy. So here's the prompt, and I didn't come up with this, I think Steven Pinker did. So Linda is 25 years old. She just graduated college, where she was part of many social justice clubs, and she was even on the board of one. She partook in many demonstrations too. Now ask yourself, is it more probable that Linda is A, a bank teller, or B, that she's a bank teller and active in the feminist movement? So what do you think? Well, the answer is actually A. It's just a truth that it's more likely for her to be a bank teller. Now you might tell yourself, wait a second, all the things that you told me, right, that she was part of social justice club, she partook in many demonstrations, etc., those are things that tend to correlate with being a feminist. However, note that B isn't just asking you if you think it's more probable that Linda is a bank teller or a feminist. It's asking you, do you think it's more probable that she's just a bank teller or that she's a bank teller and active in the feminist movement? But for her to be a bank teller and active in the feminist movement, she must be already a bank teller. So in every case of B, where she's a bank teller and active in the feminist movement, then she will also just be a bank teller. Right? This is because B is a conjunction. And this is called the conjunction fallacy. So let's look at the two arguments side by side. In one, we have the premises, Linda is 25 years old, she was part of many social justice clubs, etc. Therefore, she's a bank teller. Versus the same premise, therefore, she's a bank teller and a feminist. Okay, so the conjunction fallacy refers to the common tendency of humans to overestimate the likelihood of conjunctions, which are and statements, especially relative to their component conjuncts. Right? Remember, if Linda is a bank teller and a feminist, she is necessarily a bank teller. So this is a clear mistake. So when people pick B in this example, then they're making a clear mistake. They're making the conjunction fallacy because, again, every time, every case, or every possibility where Linda is a bank teller and active in the feminist movement, then she's necessarily going to be also a bank teller. So A is one which we might call a weaker argument. It's just saying that she's one thing, whereas B is saying that she's two things. What inductive logic, and really already our ability to put this argument into truth tables, will allow us to do is to see this conjunction fallacy. And in some cases, right, maybe if you picked the right answer here, in some cases it might be somewhat obvious to you that it's A was more likely than B. But in many cases, especially as it becomes more complicated, and in our lives we make quite complicated inductive inferences, we want a way to know which one is actually the right answer. And inductive logic will allow us to do that. Okay, so we've seen the conjunction fallacy. Let's move on to another kind of fallacy that we often make as human beings. A Boeing 747 has around 6 million parts. I think that's true. Suppose that each part is very reliable and only fails with 0.0001% chance. So it's very unlikely for any part to fail. Now, assuming that failures are independent events, and that means assume that, for example, if a screw pops off, that doesn't affect if all the other screws work properly. So assuming that these are independent events, what's the probability that all the parts work properly? So maybe pause the video and try to figure out or just come up with a number yourself. And if you've written it down, you might be surprised to find out that the answer is 0.25% chance. So it's actually very, very unlikely that all the parts work properly, right? Aviation, I know Boeing has a lot of problems, but aviation is generally very safe, so planes are built to take on these failures. But you notice that you probably put a much higher chance for all the parts working properly. But underestimating this probability is a case of what you might call a disjunction fallacy. So remember, we just saw the conjunction fallacy. This is the disjunction fallacy. The disjunction fallacy refers to the common tendency of humans to underestimate the likelihood of disjunctions, which are or statements, especially relative to their component disjuncts. So why might we fall victims to the disjunctive fallacy? Looking at truth tables, a tool we already have, can help us see this. So why is it that people think that the disjunction is true? And remember that in the Boeing example, it was a disjunction, right? You can imagine as part 1 failing or part 2 failing, etc., etc. What people tend to think is that for the conjunction to be true, all the disjuncts need to be true. But as we've seen in our truth table lectures, is that you just need one of the disjuncts to be true, and there's many, many cases of this, right? This is a case where we only have, for example, 2 parts, but imagine this truth table with 6 million tables, and the amount of true disjuncts of P and Q is going to be very large. Okay, so what are some takeaways from the conjunctive and disjunctive fallacy? One is that the weaker an argument's conclusion, the greater the argument's inductive strength. So an argument having a weak conclusion means that you're arguing for less. So in the case of Linda and the bank teller, right, making the inference that she's a bank teller is weaker than making the inference that she's a bank teller and a feminist, because you're saying less when you're saying that she's just a bank teller. The second takeaway is that humans have a tendency to overestimate the probability of long conjunctions and underestimate the probability of long disjunctions. So, you can already, having noted this fallacy, maybe reason better in your day-to-day life. And our inductive logic system is going to give us a way to systematize this. So let's look at one last kind of mistake that humans often make in reasoning. And this isn't a kind of weird philosophical example, it's actually generally a kind of example that is taught in introduction to statistics classes. and it's a surprising conclusion. So suppose we have a pretty reliable test used to diagnose a disease. 99% of people with the disease will get a positive test result, and 99% of healthy people test negative. So this is actually a very good test for a disease. It's actually much more reliable than many tests actually available for all sorts of diseases. But now, suppose that the general prevalence of the disease in the population, and this is called the base rate, is 1 out of 100. So about 1 in 100 people have this disease. So it's not all that common, but it's not ridiculously uncommon. How likely is it that a random person who gets a positive test result actually has the disease? Again, pause the video and try to come up with an answer. You might be surprised. The answer is 50%. Now, this might be really surprising to you because we just saw that the test is really reliable, has 99% of people with the disease gets a positive test, and 99% of healthy people test negative. But if you pick a random person in the population and they test positive, the probability that they actually have the disease is 50%. And this fallacy is called the base rate neglect. And I'll show you this with probabilities, why it's the case in future lectures, but I'll give you just an intuitive feel for it now. Suppose here that we have a population of people, and the people with the disease have a frowning face, and the people that don't have the disease have a smiley face. And suppose our test is pretty reliable, in meaning that 4 out of 5 people that have the disease will test positive for the disease, and 1 person out of 5 who has a disease will test negative. Okay, so the people in the red box have tested positive for the disease accurately, and 1 person has tested negative for the disease even though they actually have it. Now suppose you test the healthy population, and again suppose that it's pretty reliable such that most people that don't have the disease don't test positive, so they test negative. That's the green box. And some healthy people have what's called a false positive, which is the smiling faces with the red box. But now ask yourself, given that people have tested positive, what's the probability that they have the disease? So here you should just look at people in the red box. And actually, here it's more likely that if you're just a random person that was picked and you test positive for the disease, you'll see that there's 6 smiling faces. That means there's 6 healthy people that tested positive and only 4 that tested positive and actually have the disease. So it's more likely that even though you tested positive, you don't actually have the disease. So the takeaway here is that you shouldn't ignore base rates, right? Because why this works is because only a few people in the population actually have the disease. So you shouldn't ignore these base rates, and you shouldn't confuse the support P provides Q with the support Q provides P. Now, again, in the next lectures, we're going to show this mathematically and prove why this is the case. I hope I've shown it to you intuitively. Okay, so here's a summary of what we've seen today. We've seen that humans are prone to assign the wrong inductive strength to arguments in all sorts of cases. What does that mean? That means we're prone to make many mistakes in reasoning, and that our intuitions are often not sufficient. And there are many real-world cases where this is the case, and important ones, for example, if you test positive for a disease. So how can we decrease these sorts of mistakes? Well, we're going to do it with inductive logic, and we've motivated the project with showing some local cases of mistakes that humans are really prone to make. And inductive logic allows us to get away from this habit and actually reason better. Thank you very much. I'm looking forward to the next lecture.